This problem here is 3 parts, asking some different questions about how many moles of N2O5 will remain and how long it will take for the quantity to drop, as well as what the half-life is at 70 degrees Celsius. And we're provided with this information. We're given the reaction and a temperature with a rate constant and an initial number of moles as well as volume. So let's start out with the first question here. So what we can do is use the equation, the final concentration equals the initial concentration, and I'll mark that with a 0 down here, times e to the negative k, where k is the rate constant, times the time in seconds. And we'll save this equation because this is going to be useful, I think, for all of these parts, especially the half-life equation. So we can look at now what information we're given, and it asks how many moles will remain. So we want to make sure the numbers here are all in moles, and remain means we're going to be solving for the final concentration. Now we're provided with a starting value of moles for the gas, and what we're actually going to need to do first is convert this to molar because we're given a volume, and then we're going to use that volume later to convert the final concentration of N2O5 back to moles. So to start out, let's find this initial molar value. So we'll have our concentration, our initial concentration, equals 2.10, this value here, times 10 to the negative 2 moles. And we're going to divide that by our volume, which is 1.7 liters. So that's going to give us, let me grab my calculator really quickly. It's going to give us 2.1 times 10 to the negative 2. Whoops. Actually, I'll just manually do it. It's 0.021 divided by 1.7 give us 0.01235. So it's like a 7. 1, 2, 3, 5 molar. And now we can plug these values in to find the final concentration. So a final concentration equals 0.01235 molar times e to the negative, and our k value will be this rate constant, 6.82. 6.82 times 10 to the negative third, second to the negative 1, times t, which is, in this case, 7 minutes. So to find t in seconds, which is what we need, we'll do 7 minutes times 60 seconds per minute, and seven times 60 should be 420. 420 seconds. So times 420 seconds, and these units will cancel. And actually, let me use another online calculator here. This will make things a lot simpler than trying to use that system one. So we have here, let me make this window a bit smaller. We have 0.01235 times e to the negative 6.82 times 10 to the negative 3 times 420, and this, that looks right. So we have 0.0007, and the only unit left is molar. Now, to get it back into moles, we'll do times, this is the same as moles per liter. We'll do times our volume, which is 1.7 liters, and .0007 times 1.7 is 0.000119 moles, which is the same as 1.19, or you could say 1.2 times 10 to the negative third moles. So this one is 1.19 times 10 to negative third moles. And now I will continue with the second part as soon as I clear out a little bit of space here. I'm going to save this equation at the top here. Let me get another color for the second one. So how many minutes will it take for the quantity of N2O5 to drop to 1.9 times 10 to the negative 2 moles? So this time, instead of solving for this value, we're going to need to rearrange and solve for t, because it's asking for time, and it's asking for minutes instead of seconds. So I should keep that in mind and convert it when I need to. So let's see, we can take the concentration of A over the initial concentration, and A just is N2O5 in this case. We could write, I could probably write it as concentration of N2O5, the final concentration over the initial concentration. It's the same in the last problem I did. For the purposes of simplicity, I'll just make these equal to each other. And so we'll have this equals e to the negative kt. And if you've ever worked with logarithms, you know that the natural log of e to the whatever value just equals that value. So that'll make things a little bit simpler here. So we can take the natural log of both sides, so the ln of A over A0 equals negative kt, and if we divide both sides by the negative rate constant, then we're just left with t on this side. And now we can begin to plug some values in to this equation. So we have that the final concentration is 1.9 times 10 to the negative 2, to negative 2 moles, and we are given the initial concentration here of 2.1 times 10 to the negative 2. So our initial is 2.10 times 10 to the negative 2 moles. What else? We have the constant is 6.82, so our rate constant, and we're going to have negative k, so that equals negative 6.82 times 10 to the negative third times 1 over seconds. And I think we now have everything, and we can just put it all together really quickly and get our answer, and then we will convert back to minutes from seconds. So take the natural log of, let's see, 1.9 10 to the negative 2 over 2.1 times 10 to the negative 2. And we're going to divide all of this by negative 6.82 times 10 to the negative third times 1 over seconds. Seconds are going to move up to the top, so we can cancel that. We can also cancel these 10 to the negative 2 values, and I will now put that into my calculator up here. So we have, here, let me get this thing out of the way at the bottom here. Let's see, and back to the calculator. Okay, so we will take the natural log of 1.9 divided by 2.1 and divide that by, just put these to make sure, parentheses to make sure it knows what I'm saying, minus 6.82 times 10 to the negative third, and that gives us 14.675 seconds times, then to get to minutes, 1 minute per 60 seconds, and 14.675 divided by 60 will give us about 2.245, 0.245 minutes. So this is 0.245 minutes. Okay, and now we will continue with the third question here about half-life. And this one is takes a little bit more equation moving to figure out, but it shouldn't be too bad. Let's get a nice maybe like a green color here. Okay. What is the half-life of N2O5 at 70 Celsius? Now, we don't have to worry about temperature. These two temperatures are the same, so we can have what we're trying to solve is where our final concentration will be equal to the initial divided by 2, because it's half-life, so this is the same as 1/2 concentration initial. And we have a initial concentration of, let's see, initial would be this one, 2.1 times 10 to the negative 2 moles. So we have 2.1 times 10 to the negative 2 moles divided by 2 is going to equal our, actually, I'm thinking we might want to get this into molar. It might make our life a little bit easier in a minute. So I'm going to go ahead. Well, you know what? Actually, it probably will work out fine this way. So let me try this, and if I mess myself up, I can always change to molar. This should work. So 2.1. Let me bring up the calculator again. 2.1 times 10 to the negative 2 is the same as 0.021. 0.21 divided by 2 is 0.0105 equals 0.0105 moles, and this is our final concentration. And now that we have these two values, what we can do is calculate using this equation, move it around to again solve for t. So 1.9, we'll have, well, I'll write this out again in terms of t. So that we'll have the natural log, the initial concentration divided by the final concentration over negative rate constant equals t. And there's no units on here, so we'll just go ahead and leave it in seconds. We could do the same conversion back to minutes if you wanted to. We'll just leave it in seconds for now. So we have A is 0.0105 moles, and we have 2.1 times 10 to the negative 2 moles And actually, looking at this, we could have actually probably just put in 1/2 here, because this, well, let's see. This is the A concentration, or the, yeah, we could have put in 1/2 here instead, and I think it would work out the same way, but it doesn't really matter. We can continue this the same way. So negative K, or this will be negative, where was it? 6.82 times 10 to the negative third. So negative 6.82 times 10 to the negative third. And I forgot the natural log here. And so we're going to be left again, oh, and this is seconds to the negative 1. Again, we'll have seconds up here as our unit. And so we'll have, let me bring up that online calculator one more time. I'll make our lives a little bit simpler. The natural log of 0.0105 divided by 2.1 times 10 to the negative 2. And we're going to divide this whole thing by negative 6.82 times 10 to the negative third. And we will have, let's see, this looks a little bit off to me. We'll have, let me see. We have, did I put these values all in right? Oh, this might be part of it. No, it still looks a little bit high to me. Times 10 to the negative 2. Did get all the values in right, I think. No, this is right. I was thinking it should be smaller, but I think this is actually right. So 101. I'll check it again, my work again after this video, and if for some reason it didn't come out right, I will redo it, and you'll never know I did it wrong. And I'll post the other one instead. But I think this is right, actually. I sort of started second guessing myself. I've probably done too many of these problems in one video for my own good. So we'll have 101.6 seconds here. And that will be our t value, 101.6 seconds. And so these are our three answers. I hope this maybe got you a little bit more familiar with how to approach this kind of problem, and how to move around this equation. So we have, again, our three answers, and so we're all done here.